A couple of loose ends. First off, some people wonder, why should a photon have momentum at all? But remember, we talked about how it is that light does in fact exert a pressure. Remember, we had an electric field moving up and down, which would cause an electron to move up and down. But that moving electron then interacts with a magnetic field. So when the electron moves up, it interacts with an electron field out of the page, giving us a force to the right in the direction that this light wave here is moving. We learned before that the Poynting vector not only described the transfer of energy, but also suggested a notion of pressure coming from the radiation. Now that's a relatively small amount. Notice that the momentum here is the energy divided by the speed of light. For a non-relativistic particle, the momentum is twice the kinetic energy divided by the velocity of the particle. With a much larger velocity like the speed of light, this becomes a small amount of momentum compared to the amount of energy. The other loose end to talk about is this peak that remains at the incoming wavelength. Somehow or another, some light is scattered away from the main direction without being shifted in wavelength. It turns out that corresponds to electrons that are very close in to the center, and are tightly to the center of an atom, and are tightly bound to the nucleus of that atom and other atoms in a lattice work. As a result, those electrons are not free, and when they collide, when the photon collides with them, it's not like colliding with a tennis ball. It's more like a ping pong ball colliding with a bowling ball. The bowling ball will essentially not recoil at all, and all of the energy stays with the ping pong ball. If we think about it in terms of our formula, instead of using the mass of an electron here, we would use the mass of at least one atom. Now, a proton is 2,000 times the mass of an electron, so an atom is going to be more than 2,000 times the mass of an electron. If it's a whole crystalline structure, it'll be tens, if not hundreds of thousands of times more massive than an electron, meaning we'll get a much smaller wavelength shift. In fact, it'll be so small we can't detect it. The change in wavelength for light scattering off the inner electrons bound tightly to the nucleus is essentially zero.